Hi, welcome back to Physics Teacher for our third tutorial in our projectile motion series. In this video, I'm going to go over how to derive the maximum range of a projectile. Alright, so let's say we're launching a projectile on a level surface. That means since the level surface, its initial and final vertical position are the same, so we can say that delta dy is going to be equal to 0. And we're going to shoot something or throw something at some initial velocity, and I want to know at what angle should I throw it at so that we get a maximum range. So to do this, let's first break up our initial velocity into components. So we have our y component, which I'll write as vi sine theta, and our x component, which I write as vi cos theta, which I just use my SOHCAHTOA trig ratios for this right angle triangle to determine. Now, let's analyze our x components. If we analyze our x components, there's only one equation we can use because there's no acceleration in x. And that's that our range, which is what we want to maximize, is going to be our horizontal velocity times the time of flight. And our horizontal velocity, I can write that as vi cos theta. And then we still have this time in there. Alright, so let's analyze our y components now. Now if we're looking at our y components, we have our vertical displacement, which will be 0, but we're going to use this equation, VIY times time plus 1/2 a, which is gravity, times time squared. Alright, now we're going to make for this problem up to be positive, but it doesn't really matter. You could make down to be your positive direction. So that means VIY is going to be positive, and a is going to be negative. So I'm going to write a as negative g, where g is going to have our value of 9.81 meters per second squared. So when I substitute what we know, so this is going to be 0, VIY is going to be positive vi sine theta times time, and a is negative g, where g is 9.8, but I'm not going to substitute numbers in yet anyways. Alright, so I know that the time of flight is not going to be 0, so I can divide through every term by the time variable. So when I do that, it's great because it gets rid of the quadratic here, so time goes and a square goes over here. And so rearranging, I get vi sine theta is equal to 1/2 g delta t. Alright, so now I have two equations here with two unknowns. Right? I don't know what theta is. I don't know what time of flight is. Don't know range either, so that's another unknown. But we want to maximize range. So let me get rid of time. So I'm going to solve for time in this equation, which is going to be our range divided by vi cos theta. And then I'm going to take that, let's call this equation 1, and I'm going to sub it into equation 2. So let's do that up here, 1 into 2. So when we do that, we're going to get vi sine theta is equal to, so we have 1/2 g, and then delta t, which I'm subbing in as our horizontal displacement divided by vi cos theta. Alright, so now I'm going to multiply both sides by everything on the denominator here. So that's 2 vi cos theta. So that's going to give me 2. Here we have sine theta cos theta. And then I'm going to have vi squared, so times by vi squared. And that's all going to equal g times our range. So g times delta dx. Alright, now this is a trig identity. This is actually equal to the sine of 2 theta. right, times by, and then we still have this vi squared, which equals g delta dx. So let's divide both sides by g, so I can solve for our range. So range is going to equal to vi squared over g times the sine of 2 theta. And this is more commonly known as our range equation. And to maximize range then, if we're looking at what angle we need to fire at, well, the sine of some angle can be between 0 and 1. So to make range the largest, I want the sine of 2 theta to be equal to 1. Well, that's going to happen when 2 theta is equal to 90 degrees. The sine of 90 is 1. Therefore, dividing both sides by 2 for maximum range, you're going to hit at an angle of 45 degrees.